Hello, today we are continuing in our A-level physics revision series, this time looking at projectile motion. What we mean by projectile motion is when you fire a bullet or a gun or a ball into the air with a certain velocity and at a certain angle theta, and the ball will cover a trajectory which looks something like this. And depending on the velocity and the angle, the trajectory might do this. And if you fire it higher, or if the velocity is less, it might do this. It doesn't go up quite so high. And the question for us is, can we describe what is going on in that? It needn't, of course, be an up and down. You could, for example, have a situation where you kick a ball off a cliff. Here's the ball here. You kick it in that direction. What will it do? It will go something like that. And why does the projectile go up and down, or in this case, just down? In each case, it is, of course, because gravity is acting on it in a downwards direction. Of course, you could make the angle at 90 degrees, and if you were to do that, then the ball simply goes straight up and back down again. It doesn't go to the side at all because the angle theta in this case is 90 degrees, in which case it just goes up and comes back down again. And what we need to do is to establish how we calculate what is actually happening. Now, in the classical case of projectile motion, we have the ground and we have, say, a ball describing that sort of trajectory, and typically you will be given the velocity v, the angle that the ball is thrown, and you'll be told what the gravitational attraction or the gravitational force is. And you'll often be asked to calculate the distance travelled, or what's sometimes called the range, and the maximum height that the ball will get to above the ground, or above the point at which it was thrown. And we will find that if you know v, the velocity, theta, the angle, and g, the gravitational attraction, then you can calculate d or h. Now, in some questions, of course, it'll be the other way around. You might be given d and h and v and theta and asked to calculate g. Any variable is possible, but in the classic, you know g, v, and theta, and you calculate d and h. And the trick in all these projectile motion problems is to look at the initial velocity and direction, and to realise that if that's the velocity, of course it's now going to curve, but initially the velocity is in that direction and at an angle theta, then you can always resolve that velocity, because it is a vector v, can be resolved into an upwards velocity and in, as it were, a horizontal velocity. And what are the values of those? Well, it's done like this. This is v, this is theta, this is v sine theta, and this is v cosine theta. So the components of the velocity v are v sine theta in the vertical direction and v cosine theta in the horizontal direction. And the point about that is that they act independently, and so you can calculate what is happening in the upwards direction or the vertical direction and what is happening in the horizontal direction entirely independently. And then you bring them together to get your solution, and I'll show you how. Let's take this situation here, and we will assume that v, that's the initial velocity of the ball or the bullet, whatever it is 20 meters per second. We will assume that theta is 30 degrees, and we will assume that g is 10 meters per second squared. It's usually 9.81, but let's keep the maths simple and call it 10. And since we're going to need cos theta and sine theta we better just say what they are. The sine of 30 degrees is a half, or 0.5, and the cosine of 30 degrees is the square root of 3 divided by 2. That's the square root of 3 divided by 2, and that is equal to approximately 0.866. So what do we know? The vertical component of the velocity is v sine theta. V sine theta is v, which is 20 meters per second, times the sine of theta, which is sine of 30, which is 0.5, and so that's 10 meters per second, and that's the vertical velocity. The horizontal velocity is v cosine theta, which is going to be v, which we said is 20 meters per second, times the cosine of theta, which is 0.866. And that comes to 17.32 meters per second. So when you resolve this velocity of 20 meters per second at an angle theta, you find that that is equal to 10 meters per second vertical and 17.32 meters per second in the horizontal direction. Now, what is the vertical component going to do? Well, the vertical component is just going to go up and back down again, because gravity is acting in this direction, so the ball will slow and then it will pick up speed and it'll come back down again. And the question is, how long does it take to do that? And for that we need the formula that v equals u plus at. You'll find these formulae in my video on classical mechanics. V is the final velocity when the ball gets to the top, which is obviously 0 because the velocity is 0 and it then starts falling back down again. U is the initial velocity, which is the initial vertical velocity, v sine theta, which is 10 meters per second. And A is, of course, g, which is acting in the down direction. So what we've got is v is 0 equals u, which is 10. And then it's plus A, but of course it's minus g because v is acting upwards, but g is acting downwards, so therefore anything acting downwards needs a minus sign, minus gt, and that of course is 10 minus g we're going to call 10. We said that we'd make it simple. So it's 10 minus g, which is 10, times t. And that means that t is 1 second. In other words, it takes 1 second for the ball to get to the point where it stops and starts coming back down the other way. And of course, in exactly the same way, it will take 1 second to get back down to the ground again. So the total time for going up and down is 2 seconds. Remember, the 1 second was the calculation simply to go from where it's fired to where it stops. Remember, we're talking just about the vertical component. We said that we can treat these two components entirely independently. So here we are, it takes 2 seconds. Now in those 2 seconds, the ball is travelling with a horizontal component which is equal to v cosine theta. And the distance that it will travel, distance is always velocity times time, so the distance is going to be velocity, which is v cosine theta, because that's the horizontal component of the velocity, times t, which is 2 seconds. Now we worked out what v cosine theta was. It's 17.32. So 17.32 is v cosine theta. Let's do that again. We said that d is vt. The velocity in this case is v cosine theta. So d is equal to v cosine theta, that's the horizontal velocity, times the time. Horizontal velocity is 17.32 and the time is 2 seconds. And that comes to 34.64 meters. So that tells you that the ball will go a total distance of 34 34.64 meters as its range here, because in the 2 seconds the ball goes up and comes down, and after 2 seconds it's there and the ball has travelled this distance, which we just calculated as 34.64 meters. Now we want to know how high it goes at its maximum height. And for that we need the formula v squared equals u squared plus 2as. V, as we've said, is 0. That's the velocity when it gets to the top of the up and down path. So that's 0. U squared is the initial velocity, which is the vertical component of the velocity, and that's 10. So u squared is going to be 10 squared. And then plus 2as, well, it will be a minus because g is acting in the other direction. So it's minus 2 times g, which is 10 because we're simplifying it, times s, which we don't know. That is the height that we're trying to find, the maximum height of the trajectory. So now you've got 0 equals 100, that's 10 squared, minus 20s, and that will tell you that s, which is the maximum height, is 5 meters. So what this is actually telling you is that when you throw a ball at velocity 20 meters per second at an angle of 30 degrees, it will describe this trajectory. The total range we calculated at 34.64 meters, 34.64 meters, and the total height we calculated at 5 meters. It's worth noticing what happens if you throw the ball at a given velocity, so v is constant, you just change the angle. Well, we've already shown that if you throw it straight up, then it will come down again. It will not travel any distance at all. What is interesting is if you throw it up at 30 degrees, that angle there is 30, or if you throw it up at an angle of 60 degrees, you will find that the range in each case, that distance d, is the same. The maximum height, of course, will be different, but it just so happens that for 30 degrees and 60 degrees, the math shows you that the range will be the same. And that you get, for any given velocity, the maximum range, whoops, I better do it a little bit, is when you've got an angle of 45 degrees, or actually that's the angle. 45 degrees gives you the maximum. If you go at a lower angle, you might think that a lower angle would get you much further. But of course, in practice, gravity pulls you down much quicker because you haven't got so far to go. The vertical component is very small, and therefore it doesn't take very much time for the vertical component to go up and back down again, and that means that you are restricted on the amount of time you've got to cover this range in this direction. So you find that 45 degrees is the angle that gets you the maximum range for any given velocity. Well, we've covered the range and we've covered the maximum height, but what we might want to do, if we take our trajectory and we have an angle and we have a velocity and of course we have gravity acting downwards, is we might want to know the position at any point P. And the question is, can we deduce that? What, for example, is the height at any point P, and what is the distance d covered at any point P? It's worth just noticing this before we go on, that we're going to get two answers to this question because there's another point at which the height above the ground is h, and that is at point P prime. You can see that the ball is going up, it gets to its maximum height, and then it comes back down again. So any height will be mirrored, as it were, on the other side of the trajectory. So when you do equations, you will, and suppose you're being asked to find the point at which the height of the ball is, say, 4 meters above the ground, you will often find that that will deliver you two solutions because there are two places where the height of the ball is the same above the ground. When you get to the maximum height, of course, there is only one position where that happens, but there are two places where the height is the same, and as it were, that's the mirror image in each case. So how are we to find this position P? Well, once again, we do the old trick of taking the velocity v at an angle theta and resolving it into its two component parts, v cosine theta and v sine theta. And remember, the whole point about these components is that you can look at them entirely independently and then bring them back at the end. And so if we look in the vertical direction, we can say that s, which is distance, is equal to ut plus half at squared. That's another one of the formulas which I derive. It's a general one of the Newton's laws of motion formulae in classical mechanics. Well, s in this case is the height h. What is u? Well, that is the initial velocity in the vertical direction, so it's the vertical component, which is v sine theta times t. So that's ut, v sine theta times t. And then it's plus half at squared. Well, a is going to be gravity, which is acting downwards, so now we say it's minus a half gt squared. T, of course, is the time it takes for the ball to get to the position P. That's what T is. Now, what about motion in that direction? Well, motion in that direction is not, of course, affected by gravity. It just continues. So if you want to know what the distance is that you go in the horizontal direction, well, distance is velocity times time. So distance is velocity. Well, the velocity is the horizontal component of the velocity, which is v cosine theta times time. And in an exam question, you will typically be given some of these values which will enable you to calculate h or d. Because you've got a t squared in the formula here, that t squared, when you solve it, will give you two solutions. You normally get you normally get two solutions from a t squared formula. And that's why you get this one and this one. When you look, you want to find what the distance is, you will find that there are two solutions for distance, that distance and this distance, because both of those are distances which give you a height which is the same. You might be asked, what is the new velocity at point P? And that new velocity, of course, will be, let's call it v star. So new velocity. And that too has its horizontal and vertical components. Well, the horizontal component is very simple. That's v cosine theta, where theta is this angle here, because the horizontal component never changes. The horizontal component of the velocity is unaffected by gravity, so it just continues along this line. So v cosine theta doesn't change. It's v cosine theta here, and it's v cosine theta here. So the horizontal value is v cosine theta. The question is, what is the vertical value of the velocity once you get to point P? Well, the vertical value, let's call it v vertical at point P, so that's v vertical at point P, the vertical component at point P, is going to be equal to u plus at. And that equals u, which is the initial vertical velocity, which is v sine theta, plus at. Well, a, of course, is going to be minus g, so minus gt. So this formula gives you v sine theta minus gt is the new vertical velocity at the point P. And so if you want to now combine the two and find out what the new velocity is, at point, this is at point P here, we have said that the horizontal component is v cosine theta, and the vertical component is v sine theta minus gt, where t of course is the time it takes you to get to the point P. And although that looks complicated, of course you will be given values for these, so you can start solving them. And if you want to know what now we said v star, which is the actual velocity once you have taken out the resolved parts, well, you just use Pythagoras for that. V star squared is equal to this squared, v cosine theta all squared, plus this, v sine theta minus gt all squared. It's just Pythagoras. That squared equals that squared plus that squared. And again, it looks horrendous, but of course, in any problem that you're given, you will be given values of some of these factors and being invited to solve for others. And if you want to know what that new angle theta star is at point P, so in other words, at this point here, what is the angle, as it were, with the horizontal of the velocity once you get to point P, what is that? Well, the tangent of theta star, that is the tangent of this new angle, is just the this divided by this, which is v sine theta minus gt, all divided by v cosine theta. And again, as I pointed out, that looks horrendous, but almost certainly you will be given values for theta or g or t, and you just have to calculate what tan theta star is. Let's just think for a moment, what is the shape of the curve or the trajectory when the ball is thrown or the bullet is fired or whatever it may be? This is of course angle theta, and the initial velocity is v, and we get to a point P which is h above the ground, and the distance here we're going to call x, because this is the x-axis, and this distance here, h, we're going to call y, h and y, because this is the y-axis. So we want a formula that relates y and x. Well, y, as I've said, is h, quite simply. Now we're going to use the formula that s is ut plus half at squared, and in the vertical direction, s is the distance that we go up, which is y, is ut, well, u is going to be the initial component of the vertical velocity, which is v sine theta times t, that's ut, plus half at squared, well, a, as we know, is g, but it's in the downwards direction, so that will be minus a half gt squared. The value for x, however, as we've said, is much simpler. X, because no gravity applies, is simply the velocity times the time. The component of the velocity is v cosine theta times time. And that means that time is equal to x divided by v cosine theta t. Sorry, v cosine theta, we've got t already there. So t is x divided by v cosine theta. Now we put that t in this equation here. It's going to look a little bit horrible, but let's go with it and see where we get. We get that y equals v sine theta times t, but t is x over v cosine theta. So immediately you can see that the two v's cancel. Minus half gt squared, so minus a half g times t, which is x over v cosine theta, all squared. And that formula, which is essentially y equals a constant times x squared, right, because g, v cosine theta, sine theta, cosine theta, they're all constants. X is the variable, x squared and x, so y equals a constant times x squared plus a constant times x is basically what this is, and the shape, that is the shape of a parabola. So this is showing parabolic motion. So you might be given a question of this form. Here is a ball or a bullet. That's its trajectory. And there is a wall here, and the wall is 4 meters high. And the question is, usually is something of the order of, what is the velocity, or maybe what is the angle of the ball that is necessary to get over this wall that is 4 meters high? And they usually have to tell you how far away the wall is. They might say it's 20 meters away. So what do you have to do to get the ball over the wall? What is the velocity and what is the angle? Now, in fact, there are many solutions. So typically they might give you the velocity and ask you what the angle should be, or they might give you the angle and ask you what the velocity should be. So I'll just show you how generally you approach it. The first thing you can say is that in the horizontal direction, distance is velocity times time. Distance is 20. The velocity is the horizontal component, and remember that's v cosine theta, times the time it takes for the ball to get to that point there, which of course is for the purposes of horizontal movement for when we get to here. So 20 is v cosine theta, which is the horizontal component of the velocity, times the time. For the vertical component of the velocity, we use the formula s equals ut plus half at squared. You'll be familiar with this, we've done this before. S is 4 meters, that's what we want to know. U is the initial component of the velocity in the vertical direction, which of course is v sine theta times t. And then plus half at squared, well, once again, a is g, but in the down direction, so it's going to be minus a half gt squared. And once again, just notice, because you've got a t squared in the formula, you're going to get two solutions. And that's perfectly right, because there are going to be two places, two solutions for t, where the ball is at 4 meters. This one here, but of course the ball was also at 4 meters here. That's not the one you want. You want this one. So if you get two values for time, then the answer is that you want the later time, because that's when the ball has got to the further point. And just as we did before, you can say from this formula here, you can solve for t. T equals 20 divided by v cosine theta. And then you substitute that value of t in this formula here, which means you've got 4 equals v sine theta times t, which is 20 divided by v cosine theta, minus a half g, which of course is usually given as 10 or 9.81, you'll be given that, times t squared, which is 20 divided by v cosine theta all squared. And again, it looks horrendous, but remember that the v's of course cancel out here, and sine theta divided by cosine theta is tangent of theta. So it starts to simplify, but the important thing is that the exam question will give you some of these values, and you'll only have to then rearrange the formula in order to solve for the value that is unknown. And finally, I'm going to end with the sad, sad tale of the monkey and hunter, often known as the monkey and hunter theorem. It goes, this sad tale, like this. There is a tree, and hanging on the branch of the tree is a monkey. Over here is a hunter, and he has a rifle which he lines up by line of sight on the monkey. Now the hunter has not been on a physics course and doesn't realise that if he fires the rifle, the bullet is not going to go in a straight line. It is, of course, going to bend because of the effect of gravity, just as in all the other projectile motions that we have shown. And so he doesn't realise that. He simply sets his sights on the monkey. The monkey, unfortunately, also hasn't been on the physics course, but he is very bright-eyed and he watches very carefully. And as the hunter squeezes the trigger at the precise moment that the gun is fired, the monkey lets go of the branch and starts to fall to the ground. Now the question is, will the monkey be okay? Well, let's just draw in the parallel line which shows the position above where the bullet was fired. We can say that the bullet came out of the gun at a velocity v and it was fired at an angle theta. So straight away you know that you can resolve these into a horizontal component, which is v cosine theta, and a vertical component, which is v sine theta. We do that every single time. And when the bullet reaches the line down which the monkey is falling, the monkey of course will fall vertically. When the bullet reaches this line, let us say that the height of the bullet above the line on which the bullet was fired is little h. And we'll also say that the monkey was originally at a height capital H above this line here. The time it takes the bullet to get to this point here is time t. Now we can use the formula that S equals ut plus half at squared. It's familiar, we've been using it quite a lot. That means that the height h above this line here, which is the line from which the bullet is fired, is equal to ut, where u is the vertical component, which is v sine theta times t, and then minus, because gravity is acting downwards, minus a half gt squared. So that tells you how far above the line from which the bullet is fired the bullet will be at time t when it gets to this line down which the monkey is falling. And that gives you a value for h. Now, what about the monkey? Well, we can use exactly the same formula. Distance is equal to ut plus half at squared. We want to know how far the monkey is falling. Well, the distance that the monkey falls is ut. Well, u is 0 here because the monkey simply lets go of the branch. He has no initial velocity at all. So this is simply, ut is simply 0. And then, of course, he's going to be travelling downwards, so it's minus a half gt squared. So at the time the bullet gets to this point here, the monkey has fallen for the same amount of time and will have travelled a distance of minus a half gt squared. And since the monkey started off a total distance of capital H above this line, if the monkey falls by minus gt squared, then the monkey's height, sorry, the minus gt squared is here, minus half gt squared is here, then the actual height above the line here that the monkey has fallen to is going to be h minus half gt squared, because capital H was the original height and the monkey has fallen minus half gt squared. So it's h minus half gt squared. So let's remind ourselves where we've got to. The bullet is at a height v sine theta t minus half gt squared, and the monkey is at a height capital H minus a half gt squared. Are they the same height? If they are, the poor monkey has been shot. Well, this is a right-angled triangle, and the height h divided by the hypotenuse, h divided by the hypotenuse, which I'll call z for the time being, is sine theta. In other words, h equals z sine theta. What is the, and z, remember, is the hypotenuse, which is this distance here. What is that distance there? Well, that distance there is vt, because we set the bullet going at a total velocity v, and if there were no gravity, then the total distance it would travel, since it takes t seconds to travel there, the total distance it travels would be vt, assuming no gravity. So this distance is vt. So z, which is the hypotenuse, equals vt. So now we've got that h equals vt times sine theta. And if we put that into here, we get that the distance above the ground that the monkey is h, which is vt sine theta, minus half gt squared. And I'm sorry to have to point out to you that where the monkey is precisely the same as that where the bullet is. And so unfortunately the monkey gets shot. And on that sad note, I hope that's been helpful. Case of projectile motion, we have the ground and we have, say, a ball describing that sort of trajectory, and typically you will be given the velocity v, the angle that the ball is thrown, and you'll be told what the gravitational attraction or the gravitational force is. And you'll often be asked to calculate the distance travelled, or what's sometimes called the range, and the maximum height that the ball will get to above the ground, or above the point at which it was thrown. And we will find that if you know v, the velocity, theta, the angle, and g, the gravitational attraction, then you can calculate d or h. Now in some questions, of course, if v, this is theta, this is v sine theta, and this is v cosine theta. So the components of the velocity v are v sine theta, theta in the vertical direction, and v cosine theta in the horizontal direction. And the point about that is that they act independently, and so you can calculate what is happening in the upwards direction or the vertical direction and what is happening in the horizontal direction entirely independently. And then you bring them together to get your solution, and I'll show you how. Let's take this situation here, and we will assume that v, that's the initial velocity of the ball or the bullet, whatever it is 20 meters per second. We will assume that theta... Hello, today we are continuing in our A-level physics revision series, this time looking at projectile motion. What we mean by projectile motion is when you fire a bullet or a gun or a ball into the air with a certain velocity and at a certain angle theta, and the ball will cover a trajectory which looks something like this. And depending on the velocity and the angle, the trajectory might do this. And if you fire it higher, or if the velocity is less, it might do this. It doesn't go up quite so high. And the question for us is, can we describe what is going on in that? It needn't, of course, be the other way around. You might be given d and h and v and theta and asked to calculate g. Any variable is possible. But in the classic, you know g, v and theta, and you calculate d and h. And the trick in all these projectile motion problems is to look at the initial velocity and direction and to realise that if that's the velocity, of course it's now going to curve, but initially the velocity is in that direction and at an angle theta, then you can always resolve that velocity, because it is a vector, vector v, can be resolved into an upwards velocity and in, as it were, a horizontal velocity. And what are the values of those? Well, it's done like this. This is V and up and down. You could, for example, have a situation where you kick a ball off a cliff. Here's the ball here. You kick it in that direction. What will it do? It will go something like that. And why does the projectile go up and down, or in this case, just down? In each case, it is, of course, because gravity is acting on it in a downwards direction. Of course, you could make the angle at 90 degrees, and if you were to do that, then the ball simply goes straight up and back down again. It doesn't go to the side at all, because the angle theta in this case is 90 degrees, in which case it just goes up and comes back down again. And what we need to do is to establish how we calculate what is actually happening. Now, in the classical case,